This is a continuation of yesterday's or last time's lesson. So the first couple slides are going to be a repeat, and that's just to make sure that we're kind of picking up where we left off and you have the context. Anyway, does this look familiar? I hope so, right? It's what we were just talking about, right? It's just using an equation for it. Acceleration, change in velocity divided by time. And the units are meters per second per second. Do you remember what those units mean? If I say to you, meters per second, does that sound like crazy mumbo jumbo, or can you actually make some sense out of that? What do you think? Jess, does that make any sense? No. Okay. Yeah. The best way to think about acceleration is to picture your speedometer on the car. Acceleration is how fast the needle moves. Right? If you just barely touch the gas pedal, you have a small acceleration, right? And the needle just barely moves. Right? If you slam your foot down on the gas pedal, the needle flies. Right? And that means a big acceleration. And so with your car, you'd probably be measuring it in miles per hour. Right? That's what it would say. And you'd be measuring miles per hour per second. Right? If you measured the speed of the needle, it's how many miles per hour does it cover per second. Right? How much your speed increases each second. In physics, just to make it confusing, we talk about meters per second. Per second. And really the most confusing thing is that you have the term seconds in there twice. But it's just speed per second. So this is a good way to visualize it. We looked at this last time. The tortoise and the hare. You remember this story? So if the tortoise can accelerate at a rate of 1.5 meters per second, this was going to start at 0. He can accelerate at 1.5 meters per second. What that means is he gains 1.5 each second. All right, so after 1 second, he's going 1.5. After 2, he gains another 1.5. He's going 3 meters per second, 4.5, and so forth. And notice the way it's drawn, he covers a little bit more distance each time. Except right here. That's a mistake. A rabbit can accelerate faster, right? The number that I just made up was 4.5 meters per second. Sorry, I want to start him at 0. So if he starts at 0, that means after 1 second, he's accelerating. He's reached a speed of 4.5 meters per second. How fast after 2 seconds? Right? He gains 4.5 each second, right? It's easier if you just forget the units for a second. If the acceleration is 4.5, that means he gains 4.5 each second, right? So 4.5 and then 9. And then how many over here? Another 4.5 takes you, I think, to 13.5. Right, and so forth. Now notice the way this is drawn. The rabbit does cover more distance, right? He does get further down the road. But that's not really what acceleration tells us. All right, we can kind of, in a roundabout sort of way, we can use the acceleration to find the distance traveled. But really what acceleration tells us is how fast you're going after a certain amount of time. All right, and I'm saying that because one of the things I see people get confused about a lot is they confuse speed, acceleration, and distance. Right? So you can use the acceleration to find your speed. Right? You need to connect a couple dots if you need to find the distance. Do you remember what gravity does? Does this look familiar? We got to this last time, right? If I drop something off a cliff, gravity causes constant acceleration. Right? It means that each second, the speed increases by the same amount. So when you drop it, the instant you let go, it's not moving. If it falls 1 second, it's gained 10 meters per second of speed. So at the end of that first second, it's moving at a rate of 10. If it falls for 2 seconds, it's moving 20. If it falls for 3 seconds, it's moving 30, all right? That's the idea. And you should know this number. 10 is actually an approximation. Right? The better number is 9.8. Honestly, you can get away with 10 almost all the time. Right? I mean, it's only 2% different, right? And 10 is so easy to do calculations with, so it's easy to multiply and divide by 10, that usually we'll give away 2% accuracy for ease of calculation. And usually it's not a big deal. So anyway, remember, this tells you, if you know the acceleration, that tells you the speed at a given time. Do we know how far it's fallen after 3 seconds? Okay. We haven't done it yet, right? That's kind of what we're going to do today. We're going to use some ideas about motion. We're going to have to put a couple dots together, and we will be able to figure out, if we know the constant acceleration, as long as we know how fast it was going in the beginning, and we know how long it's been falling for, we can figure out how far it goes. So this, I think, is going to start the new stuff. And guys, there's a lot of equations that show up. They're pretty much common sense. Like this one. Right? It looks like a big fancy equation, right? I don't know. Does that look... It looks a little overwhelming, right? But really, it's nothing new. Here's what it is. Right? It says that Vf, do you know what the F stands for? That's your final velocity. This is your initial velocity. It says that your final speed is equal to how fast you're going plus, what's this? Acceleration times time. Isn't that your change in speed? Right? Because acceleration tells you how much you gain per second. And if you multiply that by the time, that tells you how much you gained. So basically, your final speed is just how fast you started plus how much speed you gained or lost. It could be negative acceleration, right? And that's all there is to it. We could draw it on a graph if we wanted to, but I don't think it's really all that useful. I'm going to do it. Well, it probably is useful. Let me do it. This would be, what would this point right here be? It's the initial velocity, right? It's how fast you're moving when time is 0. And then if you were to draw the graph, the acceleration, since this is a velocity graph, the acceleration would be equal to the slope. And then this would be your final velocity. So that's just kind of a way of tying it all back into y equals mx plus b. But like I said, hopefully you can look at the equation, and if you think about it a while, you can kind of see where it came from, right? Final speed is how fast you were going in the beginning plus whatever your speed changed by. And this is just showing it on a graph. Now, here's the deal. Let's say I find my final speed. Right? Sometimes it's really useful to know the final speed. But were you going the final speed the whole time? You weren't, right? In fact, you just reached that final speed that last instant that you were accelerating. So sometimes what we really need is the average speed. Do you know how to find the average speed? Think about it. If you know the initial and you know the final, what would the average be? Be right in the middle, wouldn't it? Right? And so that's what you're going to see on the next slide. But the idea is just as long as you have constant acceleration. And can I tell you something nice, guys? We're going to be working with constant acceleration all year. We're not really going to talk about changing accelerations. Right? Because constant accelerations are just what we usually have. So as long as you have constant acceleration, the middle of this line is going to be the average velocity. Right, and you probably knew that. If you had non-constant acceleration, that wouldn't be true, but we're not going to have non-constant acceleration. I don't know if you need to write this down. If you take a look at it and think about it, you may not. I'm going to put a box around it because it's a good equation. But what are you doing there? Yeah, you're finding an average, and I think you guys have been doing that quite a while in math class, right? So when you write it this way, it looks, oh, what is that? It's just finding the average. You add them up and you divide by 2. So feel free to put that down. Like I said, you will need to use this equation, but it's something that you could probably figure out on your own. I just put it up here because we want to make sure we think about it. Here's a second equation that, I don't know, I could get too crazy about this in a hurry and start talking about calculus and all that fun stuff. But I won't. This is another one that you probably, if I hadn't have confused you with all these notes and equations, you guys would have taken this for granted. You would have said, yeah, the distance is just equal to your average velocity times the time that you travel, right? That's an equation that most people, I don't know, when I was in, I think 6th grade is the first time I remember it, it was the old dirt equation, right? D equals RT. Distance is equal to the rate times the time. The only thing that changed here is we're talking about an average velocity. That's our rate. Right? So we'll put a box around this because it's really, really useful. And I will say one more thing about it, but that's not really anything new to you guys. All right? The one thing I just want to make sure we're totally clear on is no matter what your speed is, right? Let's say that I'm traveling to, I don't know, let's say I drive my car to Portland. We've all done it, right? Kind of a long day, but it's not too bad. When you drive your car to Portland, you might have an average speed on the way to Portland of 50 miles per hour. All right, that means it takes you, what would that be? That would be about 5 hours to get to Portland, kind of a slow trip. But it could happen, right? Does that mean that you're going 50 miles an hour the whole time? Of course not. You're probably never going 50 miles an hour, right? You're either on the freeway where you're going hopefully a little bit faster than that, or you're stopped at a gas station, or you're stopped for lunch in Eugene, or something like that, right? So you spend some time going faster than that, some time going slower than that. What does the average really tell you? This is important. All right, so it tells you that you would get there at the exact same time as somebody who did drive 50 miles an hour the whole time. That's what the average is. It factors in, you spend some of your time going faster than this, some of your time going slower than this, but if you were to have driven the same speed the whole way, it would have been that average speed. Right? That's going to be really useful when we're talking about things that are accelerating. Right? Because their speed's always changing, it can make it difficult to deal with. Once we know the average speed, we can just pretend that they were going that speed the whole time. All right, so that might be worth writing down. You guys want to write that down? It's a useful trick. Pretend and I don't know how you want to say this so that it makes sense to you. I'm writing kind of in shorthand here. I don't know if this will make sense. But pretend objects move at V average the whole time. That's going to be a really useful trick for solving motion problems. All right, so time to stop talking and start doing. It's like a Home Depot commercial, right? Don't they say it? Yeah, they say it. Okay, so we got a Corvette here, right? And it's going down a racetrack. A little drag race here, quarter mile. It takes 13 seconds. It's not that fast for a drag racer, I guess, but fast enough. Faster than my car would go. And we're assuming that it accelerates uniformly the whole time. What does that mean? That means constant acceleration, right? Basically, it means you can go ahead and use all the equations and the ideas that we've talked about, right? So this means constant acceleration. Good. So, let's do this problem together, and I'll kind of call on you guys to chime in and let me know what you're thinking. And then after this, we've got a second question that's real similar that you guys can kind of do on your own, and I'll check in with you afterwards. So make sure you follow this along. so that when I call on you, you know what we're talking about, but also so that you're ready for your question when it comes, all right? So the average speed of the car. How am I going to find that? What do you say, Dylan?
The average speed of the car.
Yes, sir.
With 100 meters per second, right?
Mm-hmm.
We would divide 400 divided by 13.
Yeah. Average speed is distance divided by time, right? That's the equation that was just, well, it's not quite the equation that was on the last screen. But average speed is distance divided by time. If you divided by both sides by t, it would be. So I'm going to say average speed is distance, 402 meters. And notice the way I'm showing my work here. This is what you guys need to get in the habit of doing. Divided by 13 seconds. So now it's just a calculator deal, right? Plug that into the calculator, and don't you get 30.8? I didn't do that in my head. I did it second period. Don't worry. I'm not one of those guys. It's funny how third period always thinks I'm better at calculations than second period. But that's right? Good. All right. I don't think I've talked about this with you guys yet. How fast is that? Like, how many miles per hour? The easy way to do it, and you'll be within about 10%, you'll be a little bit under, double it. So if this is close to 31 miles an hour, then it's close to 60. Yeah. Let me back that up. If this is close to 31 meters per second, you double it, and that means it's pretty close to 62 miles per hour. Right? So approximately 1 meter per second is 2 miles per hour. Right? That means that, if you're walking down the road and you cover 1 meter each second, 1 step per second, that means that you're going to go about 2 miles an hour. Right? I'm walking about 2 miles an hour right now. That makes sense. Right? So we're in the right neighborhood. So that means that a drag racer averages, we said, about 62 miles an hour. And everybody's okay with that? Doesn't that seem a little slow?
Where are you going to start off?
Yes. Talk to me more.
And you're going to go probably go up 1,200 miles an hour.
Aha. Guys, this is the average speed. Is he moving that speed the whole time? No. That's the midpoint, isn't it? Right? He spends half his time going slower than 30.8, but he's also going to spend half his time going faster than 30.8. So do you remember how to find the maximum speed? A graph might actually help here. If this is the velocity, what does the velocity start at? 0, and he's accelerating the whole time? It's supposed to be a straight line. This 30.8 is the midpoint of the line, isn't it? So what's the highest point? Twice that, right? You see that? So if I know the average speed, since he started at 0, I double it, right? So the maximum speed is going to be twice that. We can say 61.6. Is that right? Which that works out to be what, 125 miles an hour? Nah, that's a little better. How we doing? Does this part make sense, how I just jumped from 30.8 to 61.6? Okay. If you're a real equation junkie, and some people are, and it's really not a good habit, but we could use the equation where the average velocity is equal to 1/2 v final plus the initial. Right? We could use that. We know that the initial velocity was 0. We know the average velocity, and we could solve that for the final velocity. Right? But thinking through it without the equation is actually a better way to do it if we can. So the last step here, what's the car's acceleration? See this question? What do you think? How could I find that, Christian? What is acceleration? It's the change in speed. Yeah. It's the change in speed over time, right? It's how fast the speed changes, basically. So how much does my speed change in this problem if I'm driving my Corvette? You guys are going to see me on the weekend driving my Corvette. Can't even say Corvette. I'm still saying it wrong. How much does the speed of the Corvette change by? It goes from 0 through the average of 30.8 up to a maximum of 61.6, right? So the change is 61.6. So we can use this equation. Acceleration is the change in velocity divided by the amount of time that it takes. The change in velocity, well, remember technically change is final minus initial, so I could go 61.6 minus 0. But I probably don't need to do that, right? Divided that by the time. And Christian, how long does all this take to happen? Yeah. Yeah, because we said he was accelerating uniformly the whole time, right? The speed increased the same amount for each second. So come back down here. Whoop! The change in time is 13 seconds. And I think if I use my little mental calculator, don't we get 4.8 meters per second? Per second. Somebody check me on that, please. 4 points. It was. Yeah, you're right. 4.75. Okay. Thanks, Josh. 4.5 meter per second per second. Yeah. Yeah, exactly. Acceleration is change in velocity, so in this problem, I probably didn't need to put that there, right? But sometimes, like in the next problem, the initial speed won't be 0, and that's where you need it. So here's a question for you guys to try on your own here. And we'll get back together and we'll talk about this, but it's real similar. I'm just kind of piecing together those different equations. And best if we can do it without equations. So I'm back in my Corvette. Hey, I said it right. But this time I'm getting a little carried away with myself, right? Yeah. Yeah, that's right. I'm going way too fast. But I got pretty good eyes. I spot the trooper 100 meters ahead of me. I'm looking out. I'm no dummy. So I hit the brakes. I decelerate pretty quickly. See if you guys can unravel this problem here. All right? Give you, I don't know, a couple minutes. Try it by yourself for the first maybe 3 or 4 minutes, and then I'll let you check with each other, okay? Let's go. Take a look at my fine handiwork here. Oh, wait a minute. Come on now. You're gonna talk to me like that?
Yes.
Good. I admire your confidence and your irreverence and disrespect. You're right. Both these are wrong. Do you see why? What's wrong with this first one? Go ahead, Jeff. Okay, good. And it really does matter, all right? But the acceleration should be negative, right? Because the change in velocity is negative. Remember, acceleration is the change in velocity divided by the time. Well, if I want to calculate the change, up here, guys, change is always final minus initial. Well, the final is 30 meters per second. The initial was 45. So 30 minus 45, that's going to give me a negative change. Divide that up over 3 seconds. So a negative change of 15, change of negative 15. And divide that up over 3 seconds. So the best answer is negative 5 meters per second squared. That means if you were to graph it, it would be curved down. Right? All right, good. What's wrong with this one? Yeah, go ahead. Huh? Yeah, that's 3 seconds. And I got the 3 seconds right here, dude. Sha. And I got the 100 meters right here, so what's the deal? All right? Speed is distance divided by time, so why are you messing with me? Yeah.
So for number 2, that's the average speed he needs to go to not be caught by the top. Not the speed he is going.
Right. Good. So watch out for that, all right? That's a major, major red flag in here in physics because we have story problems all the time. And sometimes there's a number in there that you actually don't know for sure, right? I don't know for sure that it takes him 100 meters to decelerate. Right? The question is, does he decelerate before he goes 100 meters? And there's a real easy tendency to look in your notes and get kind of casual and say, oh, well, okay, speed average is just the total distance divided by the time. Well, I'm just going to look for a distance and a time then. Right? Be careful about that. Right? We don't actually know this distance for sure, so we got to come about it another way. What is that other way? Yeah, go ahead, Natasha. Yes, good. We know the initial velocity. We know the final velocity somewhere. Right there. Right? Find halfway in between them. Take the average. Right? Add them up and divide by 2. So the average speed is halfway in between 45 and 30. It's going to be 37.5 meters per second. That makes sense. Okay, cool. So then number 3, this is where we get back and we use that 100 meters, kind of. Will I be able to slow down before I've gone 100 meters? All right, how do I start that one? What do you think, Barrett?
Well, can't we just increase by 5 each second? Can't we just subtract 5 and then we get 40 and then you add it up to once you get to 30? I don't know if that's right.
Uh-huh.
You end up getting 150 bucks.
Okay. So I think what Barrett's saying, stick with me here, is we know that the initial speed is 45. Right? And we got 1, 2, 3 seconds. And so we know that we get down to a speed of 30. Whoops. We get down to a speed of 30 after 3 seconds, right? So talk to me about what you're saying here. You're saying basically you cover 45 meters the first second, and then you're going to cover 40 here, and then you're going to cover 35 here. And you just add those together?
Yeah, and that, well, so it takes it would take 4 seconds to decelerate to 30, right? Like, I don't know. Wow.
No, keep... Uh-huh.
I didn't go about it like on a graph. I just, since you're slowing 5 meters per second, you just...
That's not right, is it?
Yeah. Yep.
Fire drills are garbage. They're garbage. No more fire drills.